How to design a low-voltage regulator is discussed in this circuit design example. The output voltage of the regulator is shown to be equal to regulated 2-volt output, so that when we connect a load RL as shown, then we have a fixed 2-volt across that load. That's a low-voltage regulator, and the maximum current we can provide to the load depends on the high current PNP Bipolar Junction Transistor that we select in this circuit as shown as transistor T3. So the choice that you have for this one define the max current of the circuit. Now, the question is, how does this circuit work? And whether we can prove that it actually provides a 2-volt fix at the output. What are the choices of components in this circuit? So let's talk about them. At the input of the circuit, we have an unregulated supply. The only requirement here we have is it has to be at least 3.5 volt as an example. The N-channel JFET transistor T1 has the saturation or IDSS current to be equal to 27.5 milliamp. And also the pinch-off voltage or turn-off voltage, let's say, equal to 7.2 volt. That are given to us. The choice of 2.4 volt for the Zener diode shown in the circuit is intentional. So the question is why it has to be 2.4 volt. I'm going to talk about it. But when I get to that, I'll also talk about the one operational amplifier is used in this design. So in the middle of video, I'll talk about the choice of Zener diode and why for that, and also potential choices for the OpAmp. The single OpAmp used in this circuit doesn't require to be high speed, it just requires to be a good OpAmp with low offset, let's say current and low noise. And what we have also is a low current NPN Bipolar Junction Transistor T2 that provides the offset voltage in this circuit that I'll talk about. The bias of the Zener diode appears or happens via resistor R1. There is a specific reason that this resistor is selected to be 47 ohm, while R2 will be a large resistor 10 kilo ohm, as an example. Okay, so let's first see how the circuit works, and especially OpAmp here, how is it biased and whether it really provides a negative feedback needed. Okay, so the question is OpAmp negative feedback. So how does it work? Let's examine. All right, look at the positive supply of the OpAmp. Via the 680 ohm, it's connected to input unregulated supply of 3.5 volt minimum. The negative supply of the OpAmp is grounded. Okay, so it's a single supply design. Now, the output of the OpAmp, like a buffer, is connected to positive terminal. It's not a buffer, because buffer connects the output to negative terminal. But let's see what's happening here. Imagine that we have proper current going through to 2.4 volt Zener diode, so it's properly biased. If that is the case, then we have exactly the promised nominal 2.4 volt here across the Zener diode. I'll talk about that more. But nominal value 2.4 will appear at the connected positive input terminal of the OpAmp. If the negative terminal, for whatever reason, is still grounded, if that is the case, I'm just making a hypothetical scenario. So if the negative terminal is grounded, then what happens is, of course, OpAmp seeing such a delta between positive and negative, it will boost up the output voltage. And because of that, what happens is as a result of trying to boosting up the output voltage, there is a current that is increasing going through the 680 ohm to the positive supply of the OpAmp to drive, let's say, the output transistor that inside the OpAmp is connected to, let's say, the output, so that more current is provided at the output to drive up the output voltage. If that's the case, then the voltage drop across 680 ohm is increased, and it's designed in such a way that then it will provide the required emitter, so emitter base voltage for this PNP, for this PN junction of the PNP transistor, so that it turns on and it starts increasing the current that then will increase the output voltage by basically just providing more current to the branch of R4, R3, so that the voltage is then increased at this point. Since we have initially 0 volt here, and we have initially higher than 2.4 volt here, because we have 2.4 here, and there is a bias current going through R1, so the voltage here is higher. than 2.4, there is a current that is going this way. So effectively, this T2 will get biased, and we will have the nominal, let's say, 0.665 volt voltage drop across this transistor T2, which is a small transistor, small current. And therefore, what happens is, as we are increasing the voltage at this node, as the output voltage is increasing, then the voltage at negative terminal also start increasing and catching up, so that then we get a match for the 2.4 volt that is forced at the positive terminal. If for whatever reason, so we can see that the circuit actually works as a negative feedback. Positive terminal above negative, then negative terminal tries to catch up. Now, if it is the other way, let's say negative terminal slightly becomes more than positive terminal, say 2.6 volt instead of positive 2.4, that is enforced by the Zener diode for positive terminal, then what happens is OpAmp notice that the negative terminal has higher voltage, and therefore what happens is, as a result of that, what happens is we have, just to make sure that I am showing it right, so what happens is at the output of the OpAmp, we have a transistor like this. I'm just in a very inaccurate way showing what's going on. So there is a transistor like this that in order to bring down the output voltage, it would actually start dealing with the current being routed to the negative supply, or let's say the ground supply here. And the current through the positive supply will start reducing. So that means the voltage drop across 680 ohms start reducing. That means the voltage of emitter base of this PNP transistor goes down, and as a result the current goes down, which means then the voltage Vout effectively will then immediately is pushed to go down, and that exactly propagate to this node, and then further reducing the collector of transistor T2, which is the negative terminal of the OpAmp. So again, counteracting properly. As a result, it is now shown that we properly have negative feedback in this circuit by the connection and wiring, and OpAmp is properly biased. So with that summary, what I can say effectively that in this circuit, OpAmp is properly set with negative feedback, biased with negative feedback, and it will enforce the virtual short, which enforces the virtual short, and which means that we can make the assumption positive input terminal of the OpAmp has the same voltage at negative input terminal, and since positive, or let me write it this way, negative and positive have the same voltage input terminals, and the positive terminal is connected to Zener diode. Therefore, if Zener diode is properly biased, then we should have, so if Zener diode is properly biased with a proper Zener current, then we should have 2.4 volt nominal at both positive and negative terminal. Okay, so that is the part of intuitive analysis of the circuit. Now let's just do the actual analysis. So let's see what's happening with respect to the transistor T1. We have gate, voltage of gate equal to 0 because it's grounded. We have the source defined by the Zener diode current. So we have IZ. There is no, so what happens is we can make the assumption that this IZ is the dominant one. So we are going to assume that let's say the IZ is mostly passing through the 40 ohm resistor. If not, that's fine. But let's consider the scenario in which we have just voltage, let's say, of the source of the N-channel JFET. So this is Vs of transistor T1 JFET equal to R1, let's say IZ, and then we have plus 2.4 volt nominal voltage. So the question is then, how can we find IZ? The equation for an N-channel JFET transistor, as is well known, is this equation. We can write IDS, or the current of the drain source. So here is the drain, here is the source, here is the source, here is the voltage of source, and here is the IDS, or the current of drain source, is equal to IDSS, or saturation current, 1 minus V gate source, divided by voltage of pinch-off or threshold to the power 2 roughly. So I'm just neglecting other small variation. And with that said, then if I just substitute, what I get is, let me just write it here. So what I get is, I'm going to just substitute IDS equal to 27.5 milliamp. That's the IDSS given to us for the N-channel JFET. 1 minus voltage of VGS is voltage of gate minus voltage of source. Voltage of gate is 0. So we get 0 minus Vs, basically minus Vs. So that's VGS. Therefore, it becomes minus minus, so plus Vs. And then V threshold is negative number. So what is provided is absolute value of V threshold. For N-channel JFET, V threshold is negative number. So it would be minus 7.2 volt to the power 2. I am going to substitute equation 1. So let's refer to this as equation 1 into this equation here. So by that, I mean I'm going to substitute a value for Vs in this equation using equation 1. And if I do that, what I get is IDS equal to, and I'm going to neglect this very small current that I'm going to show. It's very small given the 10K resistor that we have here. So this current of IR2 is much, much smaller than the current of R1, or basically the current of IZ that is going through this. So the IDS is mainly just the Zener Diode current here. So IDS is equal to 27.5 milliamp times 1 minus. Instead of Vs, I'm going to use equation 1 as I said, which is this equation. So I'm going to just write R1 IDS. So as I said, IZ is mainly IDS. And we have minus 2.4 volts divided by 7.2 negative, which negative showed up here. So that negative is just manifested as I'm showing here to the power 2. So given that R1 is 47 ohm, I'm going to substitute that. R1 is 47 ohm. Then if we just solve this, here is volt, and then here is volt as well. So if we just solve this, given that the only unknown we have is IDS, we can solve it. It's a second order equation. So basically we just solve that, and the answer turned out to be, I'm going to write it here. IDS is roughly 10 milliamp. Okay, so we have a 10 milliamp going through this circuit here, which is more than enough to make sure that the Zener diode is very properly biased. As I said, the OpAmp is a low current OpAmp, so we don't expect much in terms of the current providing capability of this OpAmp. The PNP BJT high current transistor is the one that provides the main current at the output. So with that said, then we would like to also find the voltage of source, which now we can, because we now know how much is going through R1. So what I can say is the plus minus voltage drop across R1, therefore the VR1 is just R1 times IDS, which is then 47 ohm times, and we have 10 milliamp, which turns out to be VR1 just simply roughly 0.5 volt. So it's 0.47 volt. Okay, so that's good. Now, as a result, the voltage of Vs is simply the voltage of Zener diode, this voltage, plus the voltage drop across R1 to get to so a voltage of Zener plus the voltage of across R1 to get to the source of the N-channel JFET transistor. So Vz plus VR1, which means 2.4 volt nominal and then we have plus VR1 is 0.47. Therefore, voltage of source nominal is roughly 2.87 volt in this design. All right, so with that said, now we can find the target. Remember that because of the virtual short, we are saying that the op-amp will enforce same voltage at positive and negative terminals. So nominal 2.4 volt, then nominal 2.4 volt here as well. So we can find the voltage drop across R2 as well, because on one side of R2 we have just voltage of source. On the other side of R2 we have 2.4. So what I can find is, therefore I can say IR2 is equal to the voltage of source. So let me put it this way. IR2 is VR2 divided by R2, of course. VR2 is voltage of source for the N-channel JFET minus the voltage of negative terminal of the op-amp, V negative, divided by R2. So it is therefore 2.87 minus, we have 2.4. Of course, it's the same voltage drop across R1, so, and divide by 10K. So what we get out of this one is we, of course, get the same voltage drop, 0.47 volt, divided by 10 kilo ohm. So that means the current of the resistor number 2, the 10K resistor, is simply 47 microamp. Very small current. So that's why we are saying there is 10 milliamp going this way, while considerably less current than that, on the order of say 200 times less, IR2 turn out to be just 47 microamp. So this current is pretty smaller than IR1. IR1 is 10 milliamp as we found. IR2 is 47 microamp. So it was a correct assumption we made with the size of 10K compared to 47 ohm. Okay, so now let's get to, now that we know what's going on with respect to this, guys, let's see what we get at the output, and then I am going to talk about the choice of 2.4 volt here. So exactly what happens is the transistor T2, which is an NPN BJT transistor, is a low current one, because we just found that this is 47 microamp steady state that is going through this branch to get to the collector, and then because it's a diode formation connection for T2 effectively acting like a diode, then we just have the nominal VBE 0.65 volt at this current level that appears at the base emitter of T2, which means the voltage here, which refer to it as, let's say, Vx, is just, I'm going to write it here. So Vx is simply the nominal voltage of Zener minus the voltage of the base emitter of transistor T2, or just VBE of transistor 2. All right, so what is that? Well, now I'm going to be more accurate. Voltage of Zener diode is 2.4, but that is only nominal. The actual voltage depends on the temperature coefficient of the Zener diode as temperature of the junction of the Zener diode or temperature of the junction of bipolar transistor are changing in this circuit. That brings us to the conversation regarding the choice of Zener diode. So there are many choices available, but in this example, I'm going to rely on the 2.4 volt Zener diode as I am highlighting, which is the part number 1N5221 from, let's say, the Vishay, because mainly I'm talking about it because temperature coefficient data is available. You can go, any provider of Zener diode like ST Microelectronic or, let's say, onsemi would be good ones. In this case, 1N5221, 2.4 volt nominal, range of current, which in this case we are fine. We are going actually with a very safe range of 10 milliamp. And then you can see for temperature coefficient for 2.4, I have negative 0.085 typical percent per Kelvin for temperature coefficient. So that is the number I'm going to use. So Vx is 2.4, 1 minus 0.085 divided by 100 times delta T, where delta T is the change, and this is the temperature coefficient of Zener diode, which was referred to as percent as a function of percent over Kelvin. Okay, so that's the Zener diode. Now, what about the voltage of emitter base or base emitter for this transistor? Well, the same thing. It's known that the nominal voltage of the base emitter for T2 at this current level, so at the current level of 47 microamps, so we need to properly select T2 because it's very low current it's just a low current average T2, or let's say NPN transistor. So for that, we would say the nominal is 0.65 volt, but that is changing, as is well known, by about negative 2.1 volt per degree. So it's well known that the PN junction of the bipolar junction transistor has a negative temperature coefficient of 2.1 millivolt, or if you want to be accurate as is shown here, then it would be 2.1 divided by 1000, and then per degree C, so it would be times delta T. What is delta T? I'm going to write delta T here. So this is our 2.1 negative millivolt, and negative is here. So that's the, effectively what I'm writing here is coming from the temperature coefficient of the bipolar junction transistor. All right, so delta T, I wanted to say that delta T is simply the deviation of the junction temperature for the PN junction or for the Zener diode that are thermally connected in this design from the room temperature, roughly 300 degree Kelvin, which correspond to about 20 something degrees C, 27-ish, but it will be a rough benchmark for the delta T. So what is the meaning of this? Meaning that when the PN junction temperature or the Zener diode temperature is increasing 1 degree above the 300 Kelvin, which is the room temperature, then for both of them, given the choice of 2.4 volt specific diode that was mentioned, the nominal value of 2.4 is going to reduce by 2.4 multiplied by this number. So what I'm going to get is basically this formula, Vx equal to, so this was what I refer to as temperature coefficient of Zener diode. Okay, so then Vx is 2.4 minus 0.65. So that is basically the level shifting. We have 2.4 volt at the collector base of transistor T2, and then there is a level shift of 0.65 volt from that to emitter, which is Vx. So the nominal voltage of Vx is this value. Now we also have the what we have is minus. So let me just make sure I'm not missing. This is the correct one, so we should not miss this close bracket. So we have minus 2.4 volt multiplied by this guy, by the temperature coefficient, which means 2.4 times 0.85, so 0.085 divided by 100, and then we have minus times minus, which means plus, then 2.1 divided by 1000, and the whole thing is multiplied by delta T. So let me shift it so that I can write that delta T for the clarity. Okay, so here is and we can also change the color so that it's clear, sort of get a little bit of a, let's say, color delta here. Okay, so we have then multiplied by delta T. Delta T again is what is defined here, the deviation from the junction temperature at room temperature. Now, what is the benefit of this? It will turn out that this little thing here, which is the impact of the deviation from the nominal 0.65 volt for the base emitter voltage of the PN junction of NPN transistor, and also the variation of the Zener Diode voltage, reduction of it as a function of increasing temperature, they sort of cancel out each other. That makes sense. What is effectively happening is at positive input terminal, the Zener Diode voltage is going down as temperature is increasing, while at the negative terminal, we also have a reduction of the offset voltage, which is the base emitter voltage, almost at the same rate as temperature increasing. So by proper selection of 22.4 volt, which comes with temperature coefficient of negative 0.085% per degree Kelvin, we actually managed to match the negative 2.1 millivolt per degree C voltage drop for the transistor T2. So that's why these two track each other effectively, and therefore they cancel out. At the Vx, they sort of cancel out their effect, and that's exactly what this thing here indicates. So this delta, if you compute that, it will end up to be a very small value. So it will end up to be on the order of minus or plus or minus 0. A very small value actually. So it will end up 0.15 or 16 millivolt per degree Kelvin. So more than 10 times less than the inherent negative 2.1 volt millivolt per degree C drop for the base emitter of T2. So this is from standpoint of the practical design, it can be assumed to be nearly zero, negligible. So I'm going to say this is very negligible now. So as a result, we have therefore Vx roughly, we have therefore Vx, so as a result, just to make sure we have the right design here, therefore I can say Vx is, in this design, is just roughly the nominal value, which is this value 2.4 minus 0.065, which is 1.75 volt. Sort of independent of temperature, so nearly temperature independent, nearly temperature independent. So that's the good thing we wanted to have in this circuit. Now, what is the final result? Well, if we want to get to 2 volt at the output, given that Vx is now, as computed, turn out to be 1.75 volt. So let me just highlight it. And given that the current, I showed the current is very small, 47 microamp, that is coming, that is basically provided by the emitter of transistor T2, with the selection of, let's say, R3 to be 1 kilo ohm and R4 to be, let's say, 150 ohm, then we just have the very simple voltage divider effectively. Given the very small 47 microamp, the R4 and R3 resistors are effectively practically in series, because the current going through them is much, much larger than the 47 microamp, which is not much. So all I can say is, if we compute that, effectively what we have is as simple as this: 2.4 minus 0.65, 1.75 volt. So if you want to be accurate, I can write it this way then. I can say, so let me just get rid of this so that there is a bit more space here so that I do the final calculation. So I can effectively say here in this circuit that Vx divided by R3, which is 1K, we want to be very accurate, that's the current through R3 plus, so what we have, that's effectively the current through R3 minus the 47 microamp, that's the current that comes from R4. So this would be I R4, basically this current, I R4 times R4 is the voltage drop across R4. So, and then we can add this to Vx, which is this voltage, to get to the final output voltage. Basically, I'm just writing a KVL here. So effectively what I'm doing, let me just mention that this is effectively just the Kirchhoff voltage law, adding two voltages here. So we have KVL that I'm writing from output, V out, to the series of R4 and R3, I'm writing a KVL. So therefore, I'm saying V out is simply equal to these guys summed up together. Basically, the voltage drop across resistor R4 plus Vx, which if we compute that, we just end up figuring out 1.75 volt divided by 1 kilo ohm and minus 47 microamp. So this is obviously 1.775 milliamp, much larger than this current, and on the order of, say, easily on the order of 40 or something, close to that. And then we have R4, which is 150 ohm. We can, of course, change the value of R4 if we want a different value than 2 volts. So 2 volt can be adjusted by the proper selection of R4, let's say. And then plus the Vx, which is 1.75 volt. So if we compute that, we end up roughly close to 2 volt for the output voltage that we wanted. So I'm going to write it with the usual color I'm tracing here. So that's exactly what I wanted to show. We finally found that how the circuit is working and the proper value of the output and the involved resistors in order to get to 2 volt. So basically what it means that when V supply is minimum to 3.5 and upward, then the T1 will guarantee a sort of a constant, nearly a constant current supply to keep VZ, or the voltage of Zener Diode, 2.4 volt at its nominal value, properly biased. And then T2 acts as a level shifter to the Vx, and then Vx via the voltage divider of R4 and R3 gets us to the 2 volt at the output that we want. And transistor PNP BJT transistor T3 will provide the maximum current, let's say as large as 1 amp, 2 amp, whatever needed, depending on the specific application, and also depending on the choice of the PNP current, high current transistor in this circuit. The only recommendation that I have is it's important to make sure that especially the R1 and R2 resistors are, let's say, 1% resistors, so they are, or better, 0.5%. It's not tough. I mean, these are relatively easy to buy kind of resistors. So, and also R3 and R4 are also 1% tolerance resistors. So the variation is small, not a large one. With that said, I hope that this example is helpful to show how a low voltage regulator can be designed and analyzed, and we're just using a few transistors and one op amp and one Zener diode. Thanks for watching.